I will get too excited and I'll forget to record. So usually when we do multiple imputation, for those of you that might not have heard of it or really dived into it before, multiple imputation says you take a data set that has missing values in it. I think of it as a piece of Swiss cheese. And you use a computer algorithm that, based on all the known data, guesses at the unknown data. It does not try to guess the perfect true value, but it chooses the most likely value based on the relationship of all the variables with everybody else who's non-missing, assuming that it's missing at random. That's a big assumption. But it does it in looking at the distribution. So there's a little bit of noise in those predicted values. So it does it multiple times. So it takes your Swiss cheese data set and like photocopies it maybe 500 times, and it plugs those holes with likely values, each one of the 500 slices of cheese slightly different. And then you fit the model to every slice of cheese that's now filled in, and then you aggregate or collapse the results, called pooling the results using Rubin's rule. It's a very, very simple concept that actually computers are very good at doing, and it gives, through simulation studies, it's shown to be very, very accurate. It's a lot better than throwing out incomplete cases, and it's a lot better than only getting a single guess. There was about 5 years, I think, where every dissertation in statistics was a different imputation method. There was single value subject average, single average item average, single value item average. There was hot decking. There was all these different ways, but all of them produce at best accurate betas and crappy standard errors, if they're even, and then the worst case is they're dead wrong. So the multiple imputations came out by far as the winner. If you have missing at randoms, doing an SEM with FIML, full information maximum likelihood, and multiple imputations, those two will give you identical results. If it's missing not at random, nothing gives you the right results. There's no good method. So with the complication with multi-level data is taking into consideration the clustering. And Alejandro brought up tree methods like random forests, which are really, really great predictive models. And so you would think that they would be good for multiple imputation, and they are great for single level imputation. The problem is in random forest, one of the components is it takes a random subset of the data for each tree and a random subset of the variables to make splits. And if you're randomly selecting students, some clusters will have 1 student, some clusters will have 5 students, and it's going to break down the connection in the clusters. So there's been talk, should you randomly select the clusters and take all the students in the selected cluster if the cluster's selected? And there's been a lot of exploratory working on how to make that helpful, accurate method. I would say the jury's still out to some degree. You'll notice that some of those linked papers that I put on there, their publication dates are like 2018, 2019. This is very much a cutting edge thing that is still developing. So I was very happy to find some methodology walkthroughs and using R to do it, but I'm not sure that we've got all the bugs worked out and anyone's ready to say this is the perfect way to do it quite yet. So stay tuned. I'm sure more will come on missing data. Okay, other questions, concerns, or topics from chapter 4 we want to discuss? Okay. Here's Canvas. Oh, my mouse. Can I keep track of discussions? Let's take a peek in here. What else? What were some topics that were covered? Oh, I did. Now, don't panic. I added some links up here under the highly suggested reading. Some of this came from you guys. Some of it came from me. I'm not expecting you to go back and read all those. I updated the discussion board to include those, so next time I teach this class, they're there. Of course, you're welcome to look at them. I think they're good things to read, but don't be like, oh no, I didn't read those and include them. It's okay. I just didn't want to forget about them. So that analysis factor website that I told you is really good, has several posts that kind of fall on these topics, fixed versus random. Can you have both fixed and random? And also there's one on not centering, when to center and not center a variable. So there's two main reasons for centering variables. One is to lessen the correlation between terms in an interaction. So if you're going to have two variables interact together, if you center them, so there's multicollinearity. Multicollinearity is the term when you have two predictor variables that are correlated with each other. That's variable correlation, independent variable correlation, and that results in multicollinearity, which can be a problem. There's also what's called structural multicollinearity. And if I have two variables, say SES and sex, or because that's on the homework, or minority and SES, they might be correlated with each other, but they might be independent. But when I make their interaction, the interaction is always correlated with the main effects. And that's called structural multicollinearity. And there's nothing wrong with that. The model will be accurate in predictions, but that's why we don't interpret the p-values of main effects if they're involved in an interaction. Because the significance will probably be sucked into the interaction, and that's why the main effects we no longer interpret. If you center both the variables and then make the interaction, then the interaction is not correlated with the main effects, and you can interpret the p-values of the main effects. So that's one reason that you might want to center. The second one is to make the parameter estimates, especially the intercept, more interpretable. Especially if, so the interpretation of the intercept is that's the predicted value when all of the variables are 0. For continuous variables, 0. For categorical, the reference category. But what if one of our variables was age? The intercept would say, this is the predicted value when someone's age 0. Well, what if we're doing a study on elderly people? Does age 0 make any sense? No. And so in that case, the intercept's not interpretable. So it doesn't make any sense. We usually just ignore it and leave it in there to make it interpretable. If you center at either the average age or age 85 or age 65, an age that actually exists in your data set, then the intercept will be interpretable. So they say in here, so when is it not a good idea to center? And again, this was talked about on the discussion board. I've heard you guys talking about it. Good question. Well, since reason number one is to get rid of the structural multicollinearity for an interaction. If you don't have any interactions, you don't need to worry about centering. Reason number two was help with interpretation. So when you have an interaction, or when you have continuous dummy-coded categorical variables, or when the continuous variable does not have a meaningful 0. So another one is IQ. What if we had IQ in our model? What do IQs usually range between? What are the units? Psychology majors?
Isn't it like 90 to 110 or something?
That's the most likely range. Average is 100 on the IQ scale, most IQ scales. So would we ever expect anyone to get an IQ of 0?
No.
No. So we might want to center at 100, because then our slope still means the same thing, but now the intercept is for a person with an IQ of 100, which that's kind of like a point of reference, a IQ of 100. For elderly people in age, often we use age 65 because that's retirement age when elderly starts. So you can center at any value. It's more bang for your buck if you center at a meaningful value. The mean is like a default, but a meaningful value is even better. Because if you don't center, it's centered at 0. And 0, if it does, so if you have a scale where 0 is a meaningful value, then leave it in that original scale. So, but even if 0 is a real value, sometimes there's still a more important threshold. So we might have a depression scale that goes from 0 to 10, but an important threshold is when you hit 4, because 4 now you become clinically significant. So we might want to center at 4 because of the meaning of the value. So you should not center when you have all continuous predictors that have meaningful values of 0. You probably shouldn't worry about centering if you have no interactions. And if there are no values that are particularly meaningful, then you can do mean centering, but maybe not even that. So does that help a little bit with centering? Anyone want to ask any centering questions before we get into the examples?
I think I was sort of curious a little bit about like comparing centering versus standardization as options, and yeah, just how to choose between the two, because I think I'm more used to standardizing than centering.
Yeah, so centering usually only changes by adding or subtracting a number to everyone's measurement. Standardizing usually refers to subtracting the mean, so doing a mean center, and then dividing by the standard error or the standard deviation to get a z-score. This is most helpful if the units have no meaning whatsoever. If we're doing, so I did one project once and our outcome was dollars it costs to take care of someone with Alzheimer's, their daily cost of caregiving. Dollars have a lot of meaning, and we had changed all of them to equivalent to 2012 dollars for this paper. We kept those units because they are, you can interpret dollars per day really easily. But sometimes we might have a self-efficacy scale that someone's developed and psychometrically published, and the scores range from 1 to 47. What does a point on that self-efficacy scale mean? What are the units are kind of meaningless, but if we convert it to a z-score, we know a z-score of 0 is the mean, a z-score of 1 means 1 standard deviation above average, a z-score of -2 would put them 2 standard deviations below average. So making a standard score, a standardized score, a z-score, can sometimes make it more interpretable if the scale's units are kind of unknown. So a lot of times in psychology, we have these scales that are points, but the points are in a range and we don't really have thresholds or meaningful values or units. Sometimes they do. I know we worked with, I think it was the 3MS, the mental state exam, and people know that scale is a 0 to, I can't never keep that track of the mini mental score and the 3MS. One's a 0 to 30, one's a 0 to 100. But people in that field know that a 60 means something and a 40 means something. And so in that case, we might want to keep the original units. But if it's units that are kind of like, it's just the scale, who knows what it means, then standardizing is usually better to do. Does that help, Carter?
Definitely, thank you.
Yeah, and there it's often like, I'll do it this way, I'll do it that way, I will see, you know. A lot of it's based on the concept of the thing you're measuring and how much meaning the units have. The choice to standardize versus to center versus to not center. So I will point out this analysis factor, these points about when you should think about centering or should not worry about centering, that applies to grand mean centering. Group mean centering does something different, and we'll see an example today. Other topics or questions? Oh, the beautiful, beautiful diagram came back.
Yeah, that was great. Thanks for directing me back there.
Yeah, that was good. I mean, it's not very pretty, but at least, you know, 1, 2, 3, 4, 5, 6. You know, some people say, should I use REML or ML? And my answer is both. It depends on which stage you're at. Okay. All right. Well, let's jump into the encyclopedia. So I've gone through and I updated it and put in the knit reg. I'm so excited, yay. So that went live late last night. Let's see, we were in the nurses example last time. Did we get to the final model for the nurses example? Yes? No, we didn't, because we didn't talk about these random effects. I know that we didn't do that. Okay. We did level 1 predictors, level 2 predictors, and this time we have a level 3 predictor with random intercepts at both level 2 and level 3. Okay. So, okay, if we go back to the where's our pretty picture? Okay, so level 1 was, first step is to do the null model so you can calculate ICC using REML. Then you refit the null model with ML and add in fixed effects. You can add them level 1 and then level 2 and then level 3, or you can add them as a block, really, it doesn't matter. And that's using ML. Then this next step 4 is to start trying random intercepts. Now, big old caveat, warning sign. This step process of step 1, 2, 3, 4, 5, 6, this is if you're in an exploratory area. If you have theory that says these 3 things should be significant and there should be an interaction between these, start there. You don't have to start at the bottom and go up. This is the exploratory way to build a model. It's not the best way if you have more theory to go on. But on the homework assignment, I just threw a data set at you and said, go to, right? Sometimes we don't have a lot of theory, and this is the way to exploratorily build a model. Just warning there. Because always I'll have several students that get their data set to do their course project and they add 1 variable at a time, even though they know they want those 7 or 8 variables in there and they expect this interaction. Start with what you expect if you know anything about the phenomenon you're studying. So let's add random effects. This is where we left off last time. Pretty darn sure. Okay, so this first best so far model has all these main effects, fixed effects, and so far we only had random intercepts. How do we know it's random intercepts? In the parentheses, we only have what in front of the vertical bar? In the parentheses, we only have the letter 1. That 1 means random intercepts. So now you can add variables there to try random slopes. Now this is a 3-level model. Nurses, wards, hospitals. Because of the theory that experimental condition, that's assigned, can we remember experimental condition, whether they get the intervention or not? Was that assigned to individual nurses? It was not. It was assigned to wards in the hospital. So it's a ward level variable, but it could have a differential effect between different hospitals. So we can have a level 2 variable have a level 3 slope. The slope always has to be at a higher level than the variable. So experimental condition was measured at the ward, but we could see if it had a random intercept or random slope at the higher level hospital. Now to do that, this looks different than something you've seen before, right? So the first set of, you can have multiple sets of parentheses. Our first set of parentheses here, we have the 1 to mean random intercepts, and then the vertical bar, hospital/ward. So that means we have random intercepts for hospitals, and we also have random intercepts for wards within hospitals. But if I want to add a random slope for experimental condition, we cannot, experimental condition is a ward level variable, so the random slope must be at a higher level hospitals. And I put a 0 here because I don't want to fit another random intercept. This first set of parentheses will fit the random intercept. So this one, I only want to put the 0 in there to say not another random intercept, just a random slope. And so this was 1D, because step 1 was we were putting in the fixed effects. That was level the D model, A, B, C, D, and now we're going to call this lemur 2. Nurse lemur 2 re. Fun names. So here's my table with both of them. So these two models have all of the same stuff outside of the parentheses. So the fixed effects have the same parameters. So if we look at the top of the table from the intercept down, they have the same number of values. They might be slightly different number values, but they're all filled out. The thing that's different is down at the bottom. We have residual variance for both of them. How does the residual variance compare between these two models? Same. Here's the hospital to hospital intercept. How does that compare? What happened to it? It went up a little bit. Okay, and then ward to ward variance within hospitals. Now, you have to hunt a little bit. Sometimes the way it fits the models, they're on different lines. So notice this one is variance, ward, hospital, intercept with a colon there. Check this one down here. Ward, hospital, ward dot hospital, intercept. These are the same value, they just end up on different lines in the tables for, I don't know why. But the value in the first model was 0.34. In that second model, it becomes 0.11. It went down. And then we get this new variable, hospital experimental condition. And so it's got a variance component. So this is the new thing we added to the model. How can we judge if adding something to the model makes it fit better?
The likelihood ratio?
Likelihood ratio test. For some unknown reason, we use the word ANOVA to do that. Now, these two models were fit with REML. Why REML? Because we're changing the random effects. So if we fit REML for random effects, we have to say refit equals false, or else it will go back and redo them with ML, which the whole point was we wanted to do restricted maximum likelihood. Okay, so the number of parameters went from 10 to 11 because we added one random slope. So it's a chi-squared value of 1 times the log likelihoods by -2, you get the deviance, subtract the deviance, you get the chi-squared, and there's the magical stars on the wall test. What do these stars tell us?
There's a difference between the two models favoring
The two models are different. Which one's better?
two, more complex.
The more complex, which in this case, and it even prints it out here. Here's the first model. The second model is exactly the same, except for we have added on this random slope for experimental condition within hospital. Okay.
I have a question.
Yes.
It makes me think of like in just normal multiple regression, just OLS, like when you add more, the more predictors you add, it's always going to have a higher like R squared, not adjusted. But is this, I mean, I haven't tested that out, but if you just add in everything, like a ton of randoms and a ton of everything, isn't that always just, isn't that a ANOVA test that always just gonna keep getting more and more?
No, the deviance will always get better, but this chi-squared has degrees of freedom that equal the difference in the number of parameters. So it's like doing an adjusted square. So even if it fits better, is it statistically significantly better? Is it worth, it takes into account how many things you're adding.
Okay, so it does penalize you for
better,
like,
but we had to add 12 things. Was it really worth it?
Okay.
And that's what this likelihood ratio test is saying. It's saying how much did the fit improve? That's the difference in the deviance relative to how many parameters we had to add to the model to get that better fit. So you can think of it like doing an adjusted R squared instead of a straight up R squared, because you are right. If you add more things to the model, your R squared always gets better. If you add more things to the model, your deviance should go down. But does it go down enough to be worth fitting a more complex model? That's what this p-value is telling us. So this is saying, yes, the more complex model is worth it. So the only thing we added to make it more complex was the random slope. All right, so this is, this is our model 2, is our best model thus far. Then we're going to go ahead and try for cross-level interaction. So we have to fit that model 2 with ML, because the cross-level interaction would then be a fixed effects if we're going to do experimental condition and hospital size. Now, there are a ton of possible cross-level interactions, but this is the one we're going to try because we're going to assume that the people who care about this data is the one that's most theoretically important and viable. So why is this a cross-level interaction and not just an interaction?
Because you have a level 2 and a level 3 in this case variable.
Experimental condition is ward specific for the middle level. Hospital size is for the level 3, the hospital specific. And that's what makes it a cross-level interaction, because one of the variables is for a different level than the other one.
Sorry, quick question about the way that's out there. I always forget, and again, it's just confused. Why do you have the hospital before as a fix and then also in the interaction? Do you have to have them 2 times right there?
Right here?
No, sorry, up above it. So you have it in the interaction, then right above it on the next line above.
Okay, yes. So when I put, this is a great point, Joey. I'm so glad that you brought this up. Here I have the interaction between experimental condition and hospital size. When I put that asterisk between them, it's telling the computer, not only do I want the interaction, but I also want the main effects. So I could delete the hospital size and I could delete the experimental condition because the interaction with the asterisk is going to get them anyway, but it doesn't hurt to have them relisted. So that's a good thing to point out. You don't have to list them twice, but if you do, it's not going to do it twice. So that's a really good point to make for your formulas.
I also have a question.
Yeah.
I'm sure you've explained this already, but can you explain again what the 0 is in 0 plus?
Yep, this is Jill. It's okay. Who else had that question? What about that 0 again? Yeah, see, you're not.
I know you said that.
Yep. Okay, so what does the 1 mean in the line above it? That 1 tells us to fit a random intercept. Because we're already fitting the random intercept, we don't need to fit it again. We don't want to fit it again. So the 0 does the opposite. So if 1 means a random intercept, 0 means no random intercept. So by putting a 0 on the second one, it makes sure we don't fit the random intercept a second time.
Okay.
And notice in this parentheses, we only have hospital, there's not ward, because experimental condition is a ward level variable. It only can have a random slope at a higher level.
Got it.
Okay. It's very tricky. Yeah, this is, so multi-level modeling, interpreting them, if you look at your final table, it's the same way we do regular regression. Deciding how to write the formula, that's tricky. What's a level? What's a fixed effect? What's a random effect? Which ones do we need? That's the tricky part. That's why you don't take 1 hour workshop on this stuff. This is why we do lots of examples and lots of homework. Okay, let's see how we fit it. Now, notice down at the bottom, the random effects are the same random effects. The fixed effects are the same, except for we have now in the second model included this cross-level interaction between experimental condition and hospital size. So is that intervention more helpful in big hospitals or more helpful in small hospitals? Or is it the same regardless of how big the hospital is? That's what the interaction is trying to assess. And let's see, what do the walled test stars tell us about the interaction?
It's significant enough that we don't have to worry about the fact that it's a wall test.
Well, the wall test is very significant, but should we trust Mr. Wall test? It's a good rule of thumb to kind of look at, but it's kind of sketchy. So let's do the likelihood ratio test to for sure tell if adding that cross-level interaction fit better. And in this case, it ding, 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 ding. The wall test gave it 3 stars, and so does the likelihood ratio test. They agreed. So now this is our best model so far. So we started with our fixed effects, then we added random effects, and now we're adding cross-level interactions. And at this point, we've built our model up that's like the end. But when we fit this best so far model, it was with REML equals false with ML. We should always refit our final model with REML just to tidy it up. So here I'm fitting with REML, and here's our model, and it's got interactions. And oh my gosh, I don't want to interpret this. What's the best way to interpret it?
Make a plot it.
Plot it.
Panel.
Yes. Now we do have an interaction here. We have the interaction between experimental condition and size of the hospital. All the other variables are only main effects. So let's look at them, variables that are not this. So let's start with age. How do we interpret the effect of age here?
So I'll take a stab.
Mm-hmm.
For 1 unit of age increase,
So a year older in age.
the stress level of nurse increases by 0.02 units.
0.02.
Whatever that is.
It might be small, but it's significant. So if a nurse was 10 years older, it would go up 0.2. Not a big effect, but it is statistically significant. What does gender tell us? Gender here, I think was 0 male. 0 was male, 1 is female. So what does this tell us about our female nurses?
Female nurses compared to male nurses have a 0.46 lower score on their stress.
So keeping everything else constant, the females have a 0.5 point less stress than the males.
Which means for the age interpretation, we would have to say that's for males because that was the reference, right?
Yes, but when they're if they're not in an interaction, you can interpret them saying holding everything else constant. So if we have 2 nurses that are the same on all the other variables, age makes this much of a difference, 0.2 for every year, 0.02 for every year. And holding the age constants, age and experience and all that stuff constant, if the only difference was gender, the female would have 0.5 point less stress than the male. This this variable is years of experience. So how do we form that conclusion? What's the conclusion about years of experience? For each additional year experience, the stress level is
not much less.
0.06. So again, a small amount. Now, this is a special care ward versus a regular ward. Special care wards have stress levels that are 0.05 higher if everything else was the same. That's what we mean by controlling for all the other variables, if all the variables were the same. Now, experimental condition and hospital size, we should not look at the main effects. We should look at the main effects in conjunction with the interaction. And the easiest way to do that is plot it. So in our plot, we need to have both of those variables. Now, with the interaction plots, you have to choose one variable to be the x-axis and then another variable to make the different lines. You got to choose one. You can do it both ways, but should we put experimental condition on the x-axis or hospital size on the x-axis? It's a choice you have to make. And if you have 2 variables in an interaction, these are the questions I ask myself for deciding which one should be the x-axis predictor. If one of them's continuous, the continuous one should be the x-axis. If neither of them are continuous, the one that's ordinal should be the x-axis. If neither of them are ordinal, it should be the one with the most levels. So here, hospital size. What were the values for hospital size?
Wasn't it ordinal?
Was ordinal, is small, medium, large. What about experimental condition?
Dichotomous.
Dichotomous, it was intervention or control. So which one should we put on the x-axis?
Hospital size.
Hospital size, because it has more levels and they are ordinal. So the way we put it into the interact plot command is we put the name of the model. The pred is that main predictor that goes on the x-axis, and mod x means the moderating, the other variable that's involved in the interaction. And then interval equals true creates those bands that go around it. So we don't just get plain lines, we actually get bands around them. So here is our plot. Now, I might want to change this. This is hospital size. Oh, I think it's -1. It's centered, so it's like negative something, 1, and then, because it's NG, it's a numeric grand mean centered. So here's our 3 hospital sizes. So now that we can see this interaction, here I've tidied it up. I added some labels, and you can look at the code later if you want. But now that we have this, there we go. How would we interpret that interaction? What words would you type out or tell someone?
Hospital size moderates stress scores.
Hospital size moderates the intervention's effect
Oh, the intervention. Okay.
on stress level. In what way? Ooh. Is it helpful?
The intervention is much more effective for smaller hospital.
Yes, Chung-Soo, that's perfect. In the small hospital setting, the intervention groups had lower stress. In the large hospital, no difference really. They're totally overlapping. These are 95% confidence intervals. They're almost completely overlapping. In the medium-sized hospital, might make a difference, but only a small difference. What do you notice about the control group line? Stress is the same in the control group no matter what hospital size is. And the intervention is only successful in those smaller end hospitals, maybe a little bit in the medium, but it doesn't do anything for stress levels in the large hospitals. It's actually a little bit above, but I wouldn't actually say that it's higher because there's so much overlap at these large hospitals. So the way you interpret the interaction in a multi-level model is the same way you interpret an interaction in a single level model. You plot it and you look with your eyes and try to come up with what the pattern means. So if I was going to write the newspaper headline for this journal article that's going to go on the news, the nightly news, what is it? Breaking news. Stress levels in nurses can be reduced, but only in small hospitals. Yeah. Okay. And then I have put in here, just because this used to be one of my favorite plotting, was the SJ plot model. I like this other one better. And you can use the effects package with ggplot to make a really specific plot. But really, I like the, I'm starting to like this new package, this interactions plot package. It's really slick. I mean, how much did we have to type to make that interaction plot? Not very much. It's pretty slick. But here are some other ones that I made. Down here, interpretation. So there is evidence that this intervention lowers stress in nurses working in small hospitals and to a smaller degree in the medium hospital. The intervention did not exhibit an effect in the large hospitals. So what's the strength of this analysis? We were able to incorporate all 3 levels of clustering. We didn't pretend like the nurses were all independent. And we controlled for covariates, categorical and continuous, at all the different levels. So the heterogeneity was accounted for in terms of the intervention's effect at various hospitals. This is something we cannot do with an ANOVA. An ANOVA can only have 2 levels, and all the covariates are assumed to be at the lowest level. So we might have gotten kind of a similar story with ANOVA, but this is the appropriate technique to more accurately analyze this data because it had more than 2 levels, and we had covariates that were measured at the higher levels. Weaknesses. There is always a con. We have pros for methods, we have cons. The approach in our textbook had mean-centered variables. Are mean-centered always the way to go? Well, if a factor has more than 2 levels, it assumes that you have a linear trend, and it can make the post hoc comparisons more difficult. So that's kind of a downside. If you have categorical variables, trying to center them, especially if they have more than 2 levels, kind of a downside. So I reproduced the textbook that was in the book that this came out of. Oh, it was in the Hawks book, if you wanted to, and the deviance. Because Hawks, part of my effort here was to reproduce what Hawks put in his book. Okay, so there's a 3-level example. Woo woo. Okay. We ready for more centering examples? Okay.
I do have one question.
Yeah.
So it's back to that kind of the issue with now that we have 3 levels, and when you added in the random effects with the 0. So that kind of made sense. But the one part that I don't understand is I'm thinking back to when we just had 2 levels, like in the pupil popularity. And once we added in a random effect, which came up just kind of like that in front of the bar.
And then we didn't have a 0, and we didn't.
There was no 0, and there was no 1.
Because the 1's implied. If you don't put anything, it thinks there's a 1 there. Just
so
like
there is a 1, it's just behind.
Invisible. Just like in the fixed part, there is a 1 there even if you don't type it. The only way to get rid of the intercept is to put a 0.
Interesting. Okay, perfect. Yep.
Okay. Okay, it is. Do we want to take our break now, or do we want to? I think
Break
this
now.
is a break. Let's take a break, and we'll come back and we'll go through these 2 other centering and examples. Okay, 5 minutes. Oh, let me pause the recording.
It's talking about the
interaction with
okay.
the random units in the level.
Yeah.
So is that why we clean up the final model using REML?
Yes.
Because that interaction then becomes random.
Yes. Whew. Okay. I started the recording. We're going to dive in. The good news is we're going to go over 2 more examples specifically on centering. The good news is you've seen these examples before, but we're going to specifically hit centering of variables. And the first one I'm going to do is chapter 5 in the encyclopedia. It's centering and scaling, and it's the student popularity data set. So this is the popularity data set we started in chapter 2 of Hawks. So we're coming back to it, and we're going to add in the centering to it. Okay. So this is the same data set we had before. So here's single level regression. The thin black lines are an ordinary least squared regression ran independently 1 at a time on the classes. We've seen this type of thing. This is sometimes called the spaghetti plot because it looks like the spaghetti's falling on the floor. Okay, I've highlighted in red the line 0. if we put student extroversion into a model and get the slope for student extroversion, the slope, we'd have an intercept and a slope. But what would the intercept mean? The intercept would mean where that line would extrapolate back to hit the red line on this plot. So this, here we go. Can I zoom in just a little bit more? There. So this line right here, if I was to extrapolate it back out, it would hit this red line where x equals 0. It would have a y-intercept, oh, about at 6-ish. But this line down here, where would it intercept if I extended it? Maybe like at negative 0.3 or something. So each of these lines, if we extended them back, would have a different intercept. So that's what we're doing here. So let me come back. Okay, before we even get to that, I want to, okay. So this is the same data set, except for instead of fitting a different OLS model for each class, I fit a multi-level model with students nested in class. I don't know if you can notice it right off the bat, but these lines are a little bit flatter, I think, a little bit more consistent. And that's the idea of shrinkage, which we'll talk about next time. But for now, this is the random intercepts only model. This pink line is what we call the marginal line, the overall effect. This is what your parameter estimates tell you. And then here are the thin black lines, or each class. So here is the random intercepts. Now these lines, what do you notice about all these lines? They're all parallel. So each thin black line are the group-wise predictions, one per class. The pink line are the fixed effects. What do we let vary within class? We let the intercept vary class by class. So Joey was talking about, it doesn't make sense that it's hard, you know, why do we say that the variable is random? This variable is fixed. Well, the variable is fixed. Here, student extroversion has a fixed effects, and that slope is this thick pink line. But we are acknowledging that each class has a slightly different intercept. And the intercept, if you extrapolate these lines backwards, the intercept would be where they hit the red line, which is 0. Now, what is I have added here is this blue line. This blue line, anyone want to take a guess what this blue line is?
Where we're going to center it around?
It's the mean value. It's the average of all the students' extroversion scores. And we are going to, if we do a grand mean center, that means we're going to take, let's see, is that about 4.6? So we take 4.6 and subtract everyone's extroversion, we'd subtract 4.6. And basically all it does is it shifts the 0 line from over there to in the middle. Instead of the 0 line being over there, extrapolated way out of the zone of feasibility, it puts the axis, the x equals 0, right in the middle of the pack. So here I refit the model, centered. Oh no, this is before I centered. Okay, before I centered, what I've done here is I've extrapolated those lines, the random intercept lines back and forth. So in yellow here, I've highlighted, these are all the intercepts. Do the groups have the same intercept? No. So what I've highlighted in yellow is how much the classes' intercepts are different. See, some classes are higher, some classes are lower, but they're all kind of grouped around that average intercept. This pink, where this pink line hits the 0 axis, that is the fixed intercept. And how far above and below that each class, that's the U's, those disturbances, class-wise disturbances in the intercept. Now, let's see, how much variance is there? There's some variance here. What's going to happen to that variance if I shift the 0 from the red line to shift the 0 to the blue line? How much vertical variance is there going to be at this 0 line versus if we shift it over here to the blue line?
The same.
Yeah, there's the next picture. Did the variance change? So here's a key write down moment. If you have a random intercepts only model, what changed when we recentered? What stayed the same? If we have a random intercepts model and we grand mean center, did the slopes change?
None of that changed except the intercepts.
The intercepts themselves change because let's look at this top line. Instead of hitting here at like a little less than 5, it's hitting at 7. So the values of the intercepts change, but the values of the slope stays the same. And what about the random intercept variance? Stays the same. So if you have only random intercepts, the fixed intercepts will change, but the random intercept variance will stay the same. And the fixed slope will stay the same. I have a table with all this, I think. Okay. Now, what do we do when we standardize? Okay, so centering, we just subtract a number. So instead of being 0 over there, now 0 is at the mean value. How do we standardize? Not only do we subtract the mean, but we, what's the second part of standardizing? Subtract the mean and
divide by the standard deviation.
Divide by the standard deviation. What's going to happen to this picture if I divide by the standard deviation? It's going to change, stretch it so that the standard deviation, instead of being whatever it is, will be 1. Here, there, I standardized it. Woo! What does it look like? The same. If anything, just the x-axis units change. Not much. So centering and standardizing do almost nothing in the random intercepts model, except for change the units. Not the case in a random slopes model. Okay, so now we're going to move into random intercepts and slopes. Okay, so here I'm taking my popularity and I'm letting extroversion have a fixed effect and a random effect. So this first one, model 2, I just have the regular extroversion score. On this, and that's why it says 2 raw. This one, it says 2 sen because I'm using the grand mean centered extroversion score. See, it has a capital G on the end of the name because I made it that way up there. I'm not gonna go there. Okay, and then this model is 2 stand because notice the extroversion. What does it have on the end of it? A Z. Maybe I will go up here. Where's the... It's all the way at the top, I believe. Where did I make him? Okay, so there's the data set. Ooh, did I make you dizzy yet? I'm dizzy. Okay, here's my data set. Here's my data set. How did I make the G version? I subtracted the grand mean. How did I know it was 5.215? I asked, I said, what's the mean of the extroversion score? 5.215. What's the standard deviation of the extroversion score? 1.262. So to make the G version, I just subtracted the mean, the grand mean. To make the Z version, I subtracted the mean and then divided by the standard deviation. If we look here, here's the regular extroversion and its mean and standard deviation. What happens when I grand mean center? The mean value becomes 0 and the standard deviation stays the same. What happens when I standardize? The mean becomes 0, the standard deviation becomes 1. Okay, so just to show you that yes, I did, that's where those variables are coming from. Okay. Okay, so where are we going? Okay. Ordinary least squared. Ah, okay, here we go. Okay, what kind of model is this? Says it at the top. This is random intercepts and slopes. How can I tell? Do these lines have different intercepts? Up and down, yes. Do they have the same slope? No, we're letting them have different slopes. So this pink line would be the marginal or the fixed effects only. The black lines are the class specific slopes and intercepts. And we're letting each class have its own intercept and each class have its own slope. And here we've let them covary. So what's the relationship? The higher the intercept, the slope. The lower the intercept, what kind of slope? Higher intercept goes with flatter slope. Lower intercept goes with steeper slope. So there's actually a negative correlation with intercept and slope here. Okay. So I'm going to take these lines and extend them out. I think that's what I did next. Boom, I extended them out. See the intercept? On the original scale, here's the intercepts. How much variance is there compared to the last one? There's more variance, right? Because not only are they higher and lower, but they're fanning out. What's going to happen if I move that center line from 0, where it's red, over to the middle of the pack where it's blue? What's going to happen to the spread of the intercepts? Here it is spread out here. What's going to happen if I move this red line over to the blue line?
The spread gets smaller.
The spread gets smaller. When we have a random intercepts and slopes model, centering will change the amount of variance in the random intercepts. What if I centered it at 4? How much variance would there be? Even less, right? So the random components, those variance components can change when you center depending on if you have a random intercepts model or a random intercepts and slopes model. Okay, here's standardizing. It also changes. Okay. So that's a kind of a pictorial representation. I think there's a red box up here that has it summarized. Let's see. Haha. Random intercepts and slopes. If you have a random intercept and random slopes model, if you grand mean center a predictor, you will have different fixed effects, fixed intercept, different random estimates for the variance and covariance, but you will have the same fixed estimates and slopes and the same model fit statistics. The model fit statistics never change when you center a variable, grand mean center or standardize a variable. Never. The model will fit the same. If you standardize a predictor, your model fit statistics will, oh, there's a typo, low likelihood will stay the same. It always stays the same. But if you standardize a predictor, you will change the intercept, the fixed slopes, and the random estimates. Those will all, the numbers will change, but taken as a whole, it will fit the data the same wellness. Okay, should we see it in action in a data set? Okay. So let's go to model 4. We were looking at this model, this chapter 4 one the other day. This is the one where we were looking at, oh, here, let's just read it for a second, where we had students in classes in schools. And the students, we knew if they were male and female, we knew how many age and months, we had a vocabulary score and a reading score. Did we start this one the other day? I think we did. And then for the class, we know how big the classes were. So some classes were bigger than others. And the school, we know how big the school is by the school enrollment. And we only know SES at the school level. Is it likely that different classes have different average SESs? Yes. Is it likely that the students have different SESs? Yes. But we only have it captured at the school level. And this is usually because the only way we can get it is the percent of free and reduced school lunch or the average property tax value for the area. It's not something we generally ask our students, what's your SES status? And the third grader says, I don't know. And you ask the parent and they say, I'm not going to answer that. And the school says, we can't give you that information, right? Okay. So in this data set, we have 9 regions. I remember we talked about this, 9 regions in which there are 60 cores, in which each of our school districts, and within each of those, we have a total of 160 schools. And in each of the 160 schools, we have a total of 568 classes. And in those 568 classes, we have a total of 10,320 students. Whoa. And are we going to try to model all 5 levels? No. But we are definitely going to do at least student and either class or school or both. We don't have any variables given to us at the higher levels, so we're going to ignore them for the time being. Okay, so remember we were doing this one and we did this hexagonal plot, remember? So we're specifically looking at, our research question stems around, does reading or vocabulary predict reading level for these kids? And looking at this picture, you would say, yeah, higher vocab goes with higher reading. But we modeled it. I want to, I think it'll be quicker if I click on the menu. Where's my menu? Oh, where'd it go? Come back. Wait, oh, there we go. Okay, 4. And then I'm gonna go. So this is 4.9 in the encyclopedia. Centering predictors. We're changing the center. Centering variables measured at the lowest level only involves subtracting the mean from every value. The spread or the standard deviation is not changed. This is the most common centering we do. Although there are functions to automatically center and standardize variables, it is beneficial to manually create these variables, as it is more transparent and facilitates unstandardizing them later for interpretation. Okay, so just putting that out there. So here's our vocab, age, and school enrollment variables. Okay, let's talk about 0. Is 0 a meaningful value for vocab? There's only some kids got 0 on the vocab score, so I'd say, yeah, it's a feasible value. What about age? Is 0 a meaningful value? Are any of our kids age 0? Not even close. No newborns in the school system. What about school enrollment? Are any schools having school enrollment of 0? No. So I would say we probably need to center age or think about centering age in school enrollment. Vocab, maybe yes, maybe no. So this is how you put a centered variable in R in a model. So here, vocab, what was the center, the mean value? 4.494. So how do we center it? We subtract that number from everyone's score. So the best way to do it transparently is internally inside the model, create the centered variable. And the way you do it in R is you make a capital I, and that tells the computer inside this model, internally take the vocab score and subtract, and you have to type in the number 4.494, which we got by doing the summary statistics. Age, let's center it. What was the mean age? 107.5. This is months. by the way. This is not years. These are kids. So previously, we decided the best model had an interaction between vocab and age. So I'm taking the same model, it used to be model 5, and I'm taking both the variables in the interaction, and from each of them, I'm centering them each at the grand mean. Now, we also had decided before that vocab needed a random slope. It made the model better. You want to do this, if you are centering a variable, you need to do it for both its fixed and random factors. You shouldn't center one and not the other. You need to be consistent in your model. So we're predicting reading, where we're from vocab, moderated by age, and having a random slope for vocab. That's based on previous work we did. We decided that was the best model. That was our model 5. The only difference now is I'm centering both of my predictor variables.
And is this doing a grand centering or a group centering?
This is grand centering, because where did I get these numbers, 4.494 and 107.5?
The mean.
It was just the mean from everyone.
Okay.
Okay, so just this is grand mean centering. Now, before, when I tried to fit this model, I had gotten this message. What does that message mean? This is before I centered it.
It couldn't, well, it failed to converge. So it couldn't.
It failed to converge. That's the problem, right? So when I had fit that model 5 before, up here, where is it? Here it is. This is when I fit the model originally. Notice how I have vocab and age interacting with a random slope for vocab. When I did this, it gave me the message failed to converge. I had to add all this stuff in there to get that model to converge. Sometimes when a model has issues converging, if you center the variables, it's easier for the computer to solve it. And sometimes you'll get a message that says your variables are on very different scales. What is the scale for vocab? Oh, here it is. Vocab goes up to 11. What does age go up to? 135. The interaction means I multiply those. What do I get when I multiply 11 and 135? I get a number in the thousands. On the other end, what do I get when I multiply the lowest numbers? 0. So this interaction is ranging from 0 up into the thousands. That causes problems trying to converge the model. So if I center them, then these numbers are going to be smaller in range, positive and negative, but they're not going to be as big a numbers, and it kind of helps the computer out in the solving without having to add in a different optimizer. Okay, where are we? Okay, not 6. We're down. Oh, we're at 5S or 5C, right? 5C. Okay, here we go. So here is where we used the centered variables. So it's the same model as before, same variables in the same places, but we centered them. Okay, so I'm going to make a knitter table. Oh, I love this. It's so much handy. I only have to do it once. So I'm fitting the original model 5 and now model 5 that has centered variables. Let's see what changed and what stayed the same. Okay. Here we have the raw scale. Notice our variables are vocab, age, and the interaction. And then down here for mean centered, we have, oh, notice what it says for mean centered. It says vocab minus 4.49, age minus 107.5. And what does it say for the interaction? I don't know why it does this. It says, it has the I in the parentheses for the vocab, but it just has age without the I in the parentheses. I don't know why, but these are the centered variables. Okay, let's look at the interaction. What about the estimate for the interaction? Here it is in the raw scale. The estimate is 0.006 with a standard error of 0.002, 3 stars. What is it when we center it? The same. Now let's look at the main effect. The main effects here. They're both negative and one's significant, but the other isn't. What happens when we center? Whoa. What happened?
The significance flipped.
The significance flipped, and they both were negative. Now one's negative, one's positive. Because the scale changed. What about the intercept, the fixed intercept? It changed. Okay. Let's look at the fit statistics. What happens to our fit statistics?
The same.
They're identical. When you grand mean center, your fit statistics do not change, ever, by grand mean centering. Now, this should be the same. We should have the same number of schools and the same number of students. Let's look. What about the residual variance? Identical. Now, they're split up. We have to check them. So, like, here's the school, on both of these, school intercept. Did it change? Yes, because we have random slopes. And when you have random slopes, the intercept variance depends on where that 0 point is. So when you have random slopes, these variance components will change. But I want to focus on that the fit does not change. It's changing where the intercepts are and the scale of the units, but the model is still the same. When you center, though, this is one thing that that article on the analysis factor didn't point out. When you center variables, it often makes it easier for the computer to solve, especially if your variables are on very different scales or you end up with big numbers when you multiply them. But the interaction gives us the exact same parameter estimates and significance. The main effects changed quite a bit. Instead of both being negative, one was negative and one was positive, and this one was significant, now the other one's significant. So that changes a lot. Now we can do that performance package to compare the performance. What do you think is going to happen with the performance of both of these models? The performance should be the same. So let's see, here's our model, 5, the regular 5, and 5 with the centered variables. They're AIC and BIC, the same. R squared, conditional and marginal, the same. ICCs, the same. RMSEA, all the same. Model fits the same. So what does the model look like? Let's plot the centered variables with defaults. So our default with the interaction plot, remember we have 2 variables that are interacting, vocab and age. They're both continuous. So which one should go on the x-axis and which one should be the line type moderator? You could do it either way. It kind of depends on, is your research question about vocab or is it about age? What's the focus you want to have? But for this interaction plot, I'm going to say for the centered model, I'm going to put the vocab on the x-axis since that's my research question variable, and age as the line type moderator because that's like secondary for my research question. Here's my plot. All that writing, which isn't a lot, makes this plot. What does this plot tell us? What's the relationship between vocab and reading, and how does age affect it? Alejandro, go for it. Oh, were you not raising your hand? No. Someone else want to help Alejandro out?
Greater vocabulary has a higher effect for older students on their reading.
So we see a positive relationship where higher vocab is connected with higher reading. That's the steepest or the strongest relationship for the older age and less of a relationship for the younger age. Now, when you have the predictor variable, it will always be on the x-axis. The moderator variable, if it's continuous, it will automatically make 3 lines, one for the mean and then one for a standard deviation higher and lower. Sometimes that's not what you want. You can tell it which values you want there. So here I said, moderator is age. I want you to choose moderator values of 80, 110, and 150 because I wanted to see. And I've added the intervals back on. I wanted to choose some more strung out values so that I could see those differences more clearly. So age 150, so 150 divided by 12 is what? 10.25, so these are 10 and a quarter years old. These are about a little under 10, probably 8, you know. So you can see the difference a little bit more clearly. Now, this is a nice thing that R does. When we fit our model, remember how we internally centered the variables? Internally centering the variables makes it nice for you because it reveals that in the table. It says it's not just vocab, it's the vocab that's been centered at 4.49. But when you plot it, notice what's the vocab down here. It automatically uncenters it for you. I was able to put the ages on the original scale, not the centered scale. So that's really helpful. Okay, so there's centering. Now, the other one we talked about was standardizing. What does it mean to standardize? You both center at the mean and divide by the standard deviation. This does not mean normalizing. Standard z-scores is just changing the units. Okay, along with this, I want to let you know you don't have to only divide by the standard deviation. You can standardize by any value. You can divide by any value. So in this data set, let's look at SES. What does SES range from? It ranges from 0 to 100. I could make a z-score out of it, but since this is a 100-point scale, those units might have meaning. So I can divide by something else. I could divide by 10, and that's going to make them smaller numbers so the model fits better, is able to converge easier, but it keeps the interpretation still attached to the units. So I can scale a value. So here is, this is model 5, centered. That's just the centered one. And then notice in this one, vocab, I have centered it. Age, I've centered it. Every time I have vocab, I'm centering it. But I've also, what have I done with SES? I'm internally dividing it by 10 so that it's not on this 0 to 100 scale for the fitting of the model. And I still had to add a control statement to get it to run. So this one has just the two-way interaction between vocab and age. This one has the centered interaction between vocab and age and vocab and SES divided by 10. What about this last model here? What does it have? Grand mean centered vocab interacting with grand mean centered age, interacting with the third variable, SES divided by 10. Anytime you want to change any of those variables to center or standardize or change the units, all of those you use the capital I and then parentheses say the math you want to do to the variable. And this one needed a control statement as well. So let's compare them. Ugh. This one does not have SES in the model at all. This one has SES interacting, having a main effect and an interaction. This one has SES with a main effect, a two-way, and a three-way interaction. Whoa. Okay, how do we judge which one of these models is better? How do we judge which of these models is better? How do we know if it's worth it having SES interact with vocab or have a three-way interaction?
Likelihood test.
Likelihood ratio test. Amen, amen. Here we go. I put all three of them, because all three of them, we took model 5, and then we added SES interacting with vocab, and then we added the three-way interaction. So they're all building up. Okay, here we go. Model 5 to 6. Is it worth the complication? Jill's shaking her head yes. Alejandro gives it a thumbs up. What about going to the three-way interaction? Is that worth it? No. So what's our best model so far? 5, 6, or 7? 6. Okay. Woo! So our final model has vocab interacting with age and vocab interacting with SES. I've grand mean centered vocab and age, and I've divided SES by 10 to make it centered not at 0. Here I put the table. It's good to have a table. What's even better than a table?
A plot.
A plot. Now, to do this plot, what variables do I need in there? What variables need to be included in my plot?
Standardized vocabulary, standardized age, and your SES that's been
Divided by 10.
centered and standardized.
When you make the plot, you don't have to include those specifications, but we know we need the vocab, age, and SES. So we've got 3 of them. Are they categorical or continuous? Vocab is continuous. Age is continuous. SES is also continuous. Okay. Which one should be the x-axis?
Depends on your research question. So maybe if you're interested in SES, put that as the x-axis.
It does depend on your research question. We're going to go with vocab because that's what we've been doing all along. But the kind of the thing that we haven't seen before is we have 2 more moderators. Vocab is being moderated by age, and vocab is being moderated by SES. So the way we do it in the interact plot command is we're going to let the main predictor on the x-axis be the one we're most concerned with, the vocab. But we have 2 moderators. So the way the syntax works is we say mod x equals age, and then it lets us do a second moderator with mod 2 equals SES. So the way it works is the pred variable will be the x-axis. The mod x variable will make different line types. And if you add a mod 2 variable, it will make different panels. And if they're continuous and you don't say otherwise, it will do the mean plus or minus the standard deviation. Okay. Oh, we're out of time. We're in at 6, aren't we? Okay. If you have to go, you have to go. Here's a picture. Now, sometimes the picture, you might make it one way and it's hard to tell the difference of those lines. You can switch up. Well, number 1, you can switch what values, and number 2 is you can switch which one's moderator and which one's moderator X. So here I've done that. So we already said vocab is positively associated with reading, and we already said that it's a stronger association, steeper for older kids and flatter for younger kids. But what's the role of SES?
There's less effect.
There's less effect for?
Oh, for higher SES.
Higher SES see a flatter trajectory, but the lower SES we see a stronger association is steeper. So vocab is correlated with reading, but that's more true or stronger relationship for older kids and lower SES. The end. I don't know if you can trust this data set. I don't know if it's made up or if it's a full data set, but that's what this data set is saying. We're 5 minutes over. I'm sorry for stealing. Oh, I think we're 7 minutes over now. Questions, comments, concerns? I'll hang out for a few more minutes if someone wants to ask something in a low stress zone. And then there was one.
I had a question.
Yeah.
So I know you explained this to me multiple times.
That's okay.
But I'm confused conceptually. When you're doing the likelihood test, how do you know which models to compare to one another? Because like you already, but then you've got the new to compare.
Okay, you're breaking up. Let me
You could make
share. Let's see. Talk again. Let's see if it will go through.
And let me stop my video, and that might open some bandwidth. You are doing the likelihood test.
The likelihood ratio test.
The likelihood ratio test. How do you determine which models to compare to one another? So you've got like your already best fit model, and the models you've built off of that. But how do you know which ones compare? Because you could, do like 30 comparisons, just compare all of them.
So
that's not how we do it.
You have your best fit model so far, and you compare it to one that adds more to it. And if that's better, you stay with it. But sometimes when you were doing yours, you took your best fit model and you added this thing, or you added that thing, or you added that thing. So they have to be nested in each other to compare with the likelihood ratio test. So if you have the best model and then you have 3 options, you compare the best model to all 3 options. But you can only compare the options to each other if they're fully nested. Nested means one, the simpler one is completely contained in the more complex one.
What would be an example of like what that would look like?
Okay, so I think that when we were doing your cross-level interactions, you had your best model so far with your random slopes. And then you tried adding sector interacting with SES and sector interacting with sex and sector interacting with minority. All of those with the interaction are have nested within it the interaction with no interaction, but they're not nested within each other because either way you try to put it, one of the models has something the other one doesn't have.
Right. So then can you not do a likelihood test with those because they're
only can do a likelihood ratio test if they're nested. If the simpler one is completely contained in the more complex one.
So in that case, like if my model 10 is the original best fit, that's the only one that can get compared because that's the only one that just has sector by itself.
Right.
Okay, so then I would compare like 10 to 11, 10 to 12, 12 to 13.
10 to 13.
10 to 13. And then that's it, because even if like 11 and 12 are better than 10, you can't compare 11 and 12.
You can't, right, but you could make a 14 that has everything that was in both of those, and you compare 10, 11 to 14, or 10, 12 to 14.
Oh, okay. So like let's say 11 is sector and minority, and then 12 is sector and SES. To make
And you have one that had both of those interactions in it for number 14.
So that would be a three-way?
You can do it with two ways.
Okay, so then you would have like your general minority SES plus XF. So I'm just gonna show you my screen because it's gonna be confusing.
If you want to try it, might be able to.
Yeah, we'll see what happens there.
It was working before. It just started bogging down now. I don't know.
Yeah, and I'm not sure why, but when we're in class, I usually if I'm not sharing my like face, I'd be able to hear you better.
Yeah.
But, so
10 has just plain sector. 11, 12, and 13 are all built off 10, but they're 11, 12, and 13 are not nested with each other.
Right. So then
we decided 13's not. Let's see, minority. So which ones were significant?
So 12 and let me look at my notes.
Or if you scroll down a little bit, it should be down there. The NOVA's.
So 11's better, 12's better, and then
13
was not better.
Okay. Yeah, 13.
Any significance codes, which was kind of strange. So I wasn't sure if maybe there was something wrong with them.
13 is not better. There's no stars. Yeah,
there's the usual at the bottom, like significance.
Because they only add that if one of those is used.
Significant. That makes sense. So just 12 and 11. And so then you create a 14.
And I think you already pasted it. 13 again.
Oh, I did. Yeah.
So we're going to call that 14.
And so then we would add.
So you don't want sector with SES, but you want sector with minority and sector with SES. Yeah. Yeah.
Okay. So you can have
multiple ones. Yeah. And if this is better, then you can go ahead and do a 15th one that would maybe have three-way interactions. But I think that this is about where you start maxing out the data.
So it's a very big table.
And so you'll need to add, yeah, you can add it right there. Oh, wait, no, you don't want to do that one because 11 and 12 are not nested. Yeah.
Right.
Now you could put 11 or 12 in there, but you can't put them both.
So you could do like 10 and then 11.
Or 12. But you have to choose one or the other. You can't use 11 and 12.
But then I could do a second one that had 12.
Yeah.
Okay, so 14 is better than 11. 10 is still better than 11 is still better than 10. Which makes sense.
Yep.
So then 14 is the best.
So 14 is the best now so far. So you could try adding more to 14. This is why it's so much better to have some theory guiding you instead of just, I mean, we only have 4 variables here, and how many models can you make?
Right.
And how confident would you be in any of them once you start making so many?
So if you want to do a 3-way, then you would just do like sector, minority, SES. And then you would leave this as two-way.
I would get rid of it now because it's totally contained in or
Contained in that
repetitive.
one.
Yeah, and call that 15 maybe. And it might not, and when you knit it, it might go off the page, so you might have to make 2 separate tables. Not that I'm worried about the homework, but if in real life. So you can add 15 to both of those last 2 ANOVA statements because it's nested again. I think it needs to be LMER.
Oh, yes.
Oh, it's still better.
But that nesting thing makes sense now that we put it like that. I was confused with the nesting earlier, which is I had one that was like 10 and 12.
Yeah, if they're not nested, often the number of parameters will be the same, and so then the chi-squared is 0, and then it's like can't do it.
Yeah, it looked different, and I had remembered the one we did before. You had said one of them I couldn't do because it was nested, but then I do this one. I'm like, I'm sure one of these is nested, but I'm really not sure what she means.
Yeah.
With this specific date, but that makes sense that it's so conceptually I know what you mean, but when it's in R,
yeah, the application
meaning that like sector plus something is nested with sector is okay,
and that's why we get to practice it.
Yes.
Yep.
Okay. Thank you.
You're welcome. You're coming right along.
So we're eventually going to get there.
Oh yeah, totally. You're almost done.
All right. Well, thank you. I will talk to you later.
Okay, bye.